Policymakers are often interested in the returns to education. Informally, the question they want to answer is as follows: if a person is given another year of education, by how much will his or her starting salary increase? As with previous examples, this is a ceteris paribus question. If we succeed in holding all other relevant factors fixed, and then find a link between education and wages, we can conclude that education has a causal effect on wages. We can imagine an omnipotent social planner designing a randomized experiment to get at this issue. The planner would randomly sample a group of people from the population and randomly assign each person an amount of education. Some people are given 8 years of education, some are given 12, some are given none, and so on. Subsequently, the planner measures their wages. Such a randomized experiment is of course unfeasible because the ethical issues associated with randomly assigning and mandating education for a group of individuals are obvious. Although such experimental data cannot be obtained from measuring the returns to education, we can certainly collect observational data on educational background and wages for a large group of people by accessing surveys. Unfortunately, these datasets share a feature that makes it difficult to estimate the ceteris paribus return to education, and that is the fact that people choose how much education to attain. Therefore, education is not determined independently of all other factors affecting wage. We call this selection bias in our discussion of random experiments. When we are unable to do randomized experiments, we look for other methods in our causal inference toolbox to simulate a ceteris paribus experiment. The first of these tools we will cover in the next module is regression. The controlled regression is the second causal inference technique in our toolbox. We illustrate the idea of a controlled regression with a thought experiment on the economic returns to educational background. We want to be able to answer if schooling pays. Suppose the only things that we think matter in life, at least as far as earnings go, is years of education. This is represented graphically as such. So we consider two people's earnings, Craig's and Janine's. Craig stayed in school for 12 years, including high school, while Janine stayed in school for 8 years. Because we've assumed that all that matters for earnings is years of education, Craig versus Janine, we believe, is a ceteris paribus comparison. In practice, of course, life is more complicated, and many things cause wages to go up or down. This simple example suggests one significant complication: Craig is a man, and Janine is a woman. Women, unfortunately, are egregiously underpaid compared to men. The fact that Craig earns 70% as much as Janine may be the effect of more education, but it also reflects a wage gap generated by other things like gender. Now we'd like to control for the effects of gender on wages, so that we can solely focus on education's effect on wages. To disentangle the pure education effect from the differences in gender, we'll replace Craig with Hannah, who is also a woman, but has 12 years of schooling. Hannah and Janine become a ceteris paribus comparison, where the only variation is in the years of education and wages, giving us the familiar pattern we need to make causal statements. But we're still not satisfied, because what we're really after are general conclusions that go beyond individual comparisons like Janine versus Hannah. We're going to need to collect more data to allow for multiple comparisons. In this fictitious dataset, we collect 14 such comparisons. These are 14 women's starting salaries, each with varying educational background, plotted here in a two-dimensional scatter plot. We also draw the regression line, which can be expressed mathematically as the equation 2758x plus 20,169. X is years of education, and Y is yearly wage. We interpret the coefficient of X, 2,758, to mean that for every additional year of education, a woman earns $2,758 more in wages. This number has many names in regression. It's called a coefficient, a parameter, or an estimator. We'll just call it coefficient. If the coefficient of our interest, in this case, years of education, is a non-zero number, then that suggests to us that there might be a causal effect of education on wages. Why? Because if the coefficient was zero, then the interpretation is that for every additional year of education, a woman earns $0 more, which suggests that there is no causal effect of education on wages. Notice any problem with our analysis? Remember, our original question was to answer whether education pays, not whether education pays for women. Because we're after general conclusions that go beyond comparisons between women, we need to look for similar contrasts for men. We need two data sets of wages across years of education, one for each gender, for which we can calculate the causal effect of education on starting salary for each gender. Let's call these two, coefficient 1 and coefficient 2. Coefficient 1 is a measure of the causal effect of education for female, and coefficient 2 is a measure of the causal effect of education for male. Next, we'll calculate an average of these two coefficients to get one coefficient, to represent the fact that we want an average causal effect of education on wages for all genders. While mathematically, what we've described earlier, taking an average of coefficients derived from data separated by gender, is not exactly how the regression technique works under the hood. The concept is essentially the same. A controlled regression makes gender group-specific comparisons, then outputs a blended coefficient which has a ceteris paribus interpretation, because the coefficient is derived from the weighted average of gender-controlled estimates of the causal effect of education on wages, effectively making it a gender-neutral, or controlled effect of education on wages. Separating data on groups has a causal interpretation if you think about it, because in each group, we are comparing subjects that have the same gender, but different years of education, and we said this is exactly what we wanted to do to disentangle the pure education effect from gender differences. We want all other factors to be held equal, so that the only things that are varying are years of education and wages. And if you can recall, that's why we compared Janine to Hannah and other women. And similarly, we made sure that men were compared with other men. A method like regression that works by matching on similar values is called a matching method, and the basic idea is this: let's find people who look the same in our data, but only differ in the treatment variable. That way, we can isolate the treatment variable as the exclusive reason for variation in the outcome variable. Now if you are running a regression, you don't have to do it manually, or know what exactly goes on under the hood. Thankfully, we have statistical software that runs the regression for us. All we need to do is specify a model in the corresponding data. Here we're going to specify the regression model both graphically and mathematically. Both are equivalent, although you are probably more familiar with the graphical notation by now. One addition we will make is that we'll include a factor labeled U that also affects wages. What is this factor exactly? Well, remember we assumed that wages are determined by education and gender only, but let's be real, there's going to be more to wages than just education and gender, like caliber of school attended, race, geography, ability, and more. To represent all the unaccounted factors in our regression model that determine wages, we introduce the notation, the letter U, in our model. At this point, you might be asking, what are we doing? I just wanted to calculate the causal effect of education on wages? Why do I care about U? Again, this goes back to the discussion of ceteris paribus. Regression is a way to make other things equal, but it only does so partially, for controls are generated only for variables specified and included on the right-hand side of the model. That means we only have controls for gender. Failure to include enough of the right controls would leave us with bias. The regression version of the selection bias generated by inadequate controls is called omitted variable bias. Just to refresh your minds, we covered selection bias in the context of randomized experiments when we said that simply comparing the average health level of the insured and uninsured to derive the causal effect of insurance on health introduced selection bias because insured people are likely to be more wealthy and educated, therefore heavily biasing the causal link between insurance and health outcomes. Similarly, omitted variable bias creeps in our regression model when we don't control for all the variables that are relevant to wages, but are correlated with years of education. This is why we had to control for gender when estimating the education premium. And gender's certainly not the only variable that we have to control for to get the unbiased causal effect of education on wages. What about ability or family background? What if people who get more schooling are just smarter and come from well-to-do backgrounds? And that's why they get higher wages. Maybe school doesn't really impact wages that much, and it's actually capturing the effect of ability and family background. There's a countless number of omitted variables that are always lurking within this U factor, and the essence of regression is that we'd like to specify them, and have data on them to control for them. This is why we care about U, the group of unknown factors. Notice that we haven't been very rigid or formal in discussing which variables to include as controls, and that's because the choice of which controls to include in our model is determined partly by common sense and intuition. Just as we did with the education wage example, we started with a base model of wage being solely determined by education, and grouped all other factors into U. Then we intuited that gender would be a source of bias, which is why we added it to the model as a control. Then we thought of other possible confounders that we needed to control, like family background and aptitude, since making wage comparisons within groups that have similar family background and aptitude would be more apples to apples than they otherwise would be. Are we done now? Well, not really. We'd like to capture every important variable that can bias the causal effect of education on wages, but in practice, we cannot observe every single relevant variable. We can't control for everything, which is what ceteris paribus means, all else equal. So do we give up on ceteris paribus? Well, not necessarily. The key question that every user of controlled regression has to answer is this: have enough key factors been controlled for, or made equal across comparison groups, such that bias from the things we haven't accounted for is mostly eliminated? This is also called the unconfoundedness assumption. And admittedly, this is really hard to argue and rationalize, because you have to convince yourself and others that you've got the exact correct set of variables that, if controlled for, will actually remove most of the unaccounted variation and confounding variables. Let's head right into an example of a controlled regression being used in an actual research study. This study is by the economist Sandra, who in 1999, published a famous paper that studied whether housing prices are affected by school quality. The idea is that parents care about their children's education and therefore, are willing to pay more money for a house that is zoned in a good quality school. At a first glance at the topic of the paper, a light bulb should go off in your head. Better schools tend to be located in wealthier neighborhoods, and wealthier neighborhoods usually have amenities like parks, fitness centers, and swimming pools. That means that just looking at the effect of school quality on housing prices would yield a biased result. In fact, bias is one of the first things the author talks about in the introduction to her paper, and it reads: if the estimation strategy does not correct for observable and unobservable neighborhood characteristics, potentially correlated both with housing prices and school quality, then the estimation of the marginal willingness to pay for a better school might suffer from severe biases. Black's first attempt at the problem is a controlled regression of this model structure. The outcome variable is the home value. The treatment variable is the average test score of the primary school associated with the district the house is placed. And the controls are the various characteristics of the house like bedrooms, bathrooms, lot size, internal square footage, as well as neighborhood and school district characteristics. The causal effect of our interest is this gamma term, the coefficient attached to test score. These are the results from the controlled regression. The main finding here is that the magnitude of the test score's coefficient indicates that a 5% increase in the average elementary school test score is associated with a 4.9% increase in the house price, an increase equivalent to almost $9,200 at the mean. Is this good enough? Can we run with these results? Well, that depends on whether we believe there are enough controls to ensure that observable and unobservable characteristics which are correlated both with housing prices and school quality are controlled for. Otherwise, we would have a biased estimate of the causal relationship between school quality and home values. Black certainly thinks that the controlled regression does not suffice. This is her summary. A drawback to these approaches is that all relevant house or neighborhood characteristics cannot be observed, hence results are biased because of omitted variables. As we did before with randomized experiments, we'll note some potential downsides to using controlled regression. A big pitfall in regression is that confounders are often unobservable. Either because the variables are measurable in theory but are not available, like health information which is often safeguarded by hospitals due to privacy rules, or because the variables are hard to quantify, like attractiveness or sociability. Whichever the case, often the best we can do with regression is to proxy for those unobservables with whatever data we have access to. For example, we might very well have access to SAT scores and parental income which, while not perfect, could be a good estimate or proxy for aptitude and family background. Therefore, regression requires some cleverness on our part to come up with creative variables that serve as good proxies for the variables that we want to control for. Another pitfall is that sometimes we might get too eager about controlling for variables, that we unknowingly control the treatment variable. This is the problem of included variable bias. As an example, the journalist, Ezra Klein, wrote in an issue on Vox.com, that most gender wage gap studies try to control for so many things, that they end up controlling for the thing they are trying to measure. Klein uses the example of hours worked, which is a standard control in wage gap studies. Note that because women tend to work fewer hours than men, if a study controls for hours worked, then some of the gender wage gap would disappear, since women work shorter hours because they are usually assigned the bulk of childcare responsibilities. Controlling for hours worked, in other words, is at least partly controlling for how gender works in our society. It's controlling for the thing that should actually be allowed to vary. The lesson? We have to be pretty careful about what we control for. The controlled regression is a pretty timeless technique that has a lot of resources devoted to its study. If you want to learn more about regression, these are the resources I recommend.